Thanks for being here. I'm Yutao Zhang from Tsinghua University, and this is a joint work with my advisor, Professor Tang, Zhilin, Professor Jian, and Professor Philip Yu. So, before I go into the detail of our work, I want to first briefly mention our online system, A Miner. So, A Miner used to be known as RNet Miner. It's an academic social network analysis and mining system. It has been online since 2006 and have integrated more than 38 million researcher profiles and more than 100 million publications. It attracts more than 100,000 users from all over the world every month. So to build such a system, we designed sophisticated information extraction technologies and name disambiguation technologies to automatically construct the researcher profiles from the web. Until today, we have extracted more than 1 million researcher profiles. So, as we see, we extract affiliations, positions, telephone numbers, emails, and all kinds of information. But is it enough? The answer is no. So we can see first of all, we can see this image. So this is the A Miner profile of Dr. Shai. We can see that it shows that he is affiliated with McGill University, but it's clearly out of date and need to be corrected. And also, this information, they are distributed on different sources on the web. So to integrate this information, we need to first leverage search engine techniques to find these data sources. And however, it is only possible for us to find those authorized person, because their information is dominated on the web. And most of the personal information is actually hidden behind the deep web and hard to find by search engines. So how do we solve this? Actually, it's lucky that nowadays we have different kinds of different kind of social networks. So where users they can manually maintain and updating their personal information. So on these different social networks, they have different functionalities and hence provide different informations. So for example, on LinkedIn, we have professional information, we have a business contact, we have experience, and we have expertise and skills. And while on video lectures, we have this video contents like what we are taping right now. So if we can integrate all this information into together, we can create a more comprehensive view of a person and hence benefit many different applications. So we refer this problem as identity linking. So the problem is we want to identify users from different social networks and integrate their information together. So now let's formally define this problem. Apparently, the input of our problem is a set of social networks. And each social network, we represent it as a set of vertex V and a set of edges E. And each vertex is associated with a set of attributes. So we use the capital X to indicate the space of all the potential matchings that between different social networks, different pair of social networks. And each pair is associated with a Y, with a label Y that indicates whether or not this pair is true, that these two profiles that belongs to the same person. So basically, the problem is defined as a binary classification problem. So to tackle this problem, we propose a method called Cosnet. It stands for connecting social networks with local and global consistency. It's defined as an energy-based model So we want to find the best configuration of Y that minimize an energy function E, which depends on Y and X. So to illustrate our process, we use a toy example here. So we have 3 networks here, and each network consists of 3 vertices and 3 edges. So to link these 3 networks, we first need to consider the pairwise similarity between vertices. So here we define a set of pairwise similarity features, such as username similarity, username uniqueness, profile content similarity, ego network similarity, and social status similarity. So we model this as an energy function that is a weighted sum of all these similarities. We refer this as local consistency. And then we need to consider the network structures. So here we encourage the neighborhood preserving matching. That is, we encourage that if 2 vertices they matched as the same person, then we encourage that their common neighbor are also being matched. So to illustrate, let's go back to this example. So we can see that the vertex V11 is friended with the vertex V12 on G1. And the vertex V21 and the vertex V22, they are friends on G2. So let's consider 2 pairs, V11, V21, and V12, V21. These are 2 potential matchings. They have 3 possible configurations of the labels of them. So they can either be both true, or one of them are true, or both of them are false. So among these 3 configurations, we prefer this one to appear in our final result. And so we model this by defining 3 feature functions, where each feature is correspond to one of the states I described on the last slide. So we define a feature function, which is a weighted sum of these features. And if we are matching 2 social networks, we can get a fairly decent result by a method considering both local consistency and network consistency. But if we are dealing with multiple social networks, we need to also consider the transitivity of identities across different social networks. So it's basically like if we match the vertex V11 to V21, and at the same time we match the V11 to V31. Now, if we choose not to match V31 to V21, then there will be inconsistency. So to avoid this, let's again take a look at these 3 pairs. They have 4 potential configurations. They can either be all true, or one of them are false, or 2 of them are false, or all of them are false. So among these 4 possible configurations, the second one is what we call the inconsistent state, and we need to avoid this. So again, we define 4 features, and each corresponds to one of the states defined previously, and we add an additional energy function that is a weighted sum of these features. So finally, our objective function is defined by combining the local consistency, network consistency, and the global consistency terms. So we want to find the best configuration of Y that minimizes this objective function. Recall that we have a set of weight parameter W that need to be learned from the data. So here we use a max margin learning framework that our objective function is written as a regularized hinge loss function. And since our objective function is it involves a lot of high-order energy functions, which is intractable. So we leverage Lagrangian relaxation to decompose the original problem into a set of easy-to-solve problems. So with this dual decomposition process, the resulting objective function is convex and non-differentiable, so it can be solved by standard projected gradient descent method. I won't go into detail of the learning algorithms, but you can refer this to our paper. Now I will present some of our experimental results. So to evaluate the performance of our method, we first conducted an experiment on 3 social networks, A-minor, LinkedIn, and video lecture. So we compared a set of our method to a set of baseline method. The name match method is a trivial baseline method that is simply just matched all the accounts that with the same name as the same person. So due to the ambiguity of names, it achieves a very low precision. SVM, it trains a linear classifier based on our local features. And MNA is an extension to SVM, which it has an additional post-processing process that it ensures one-to-one matching between different networks. And sigma is a propagation-based method. It starts with a seed set and just propagates the similarity along the edges and iteratively add new mappings into the set. And the Cosnet is our method. It can be shown that our method outperforms these baselines significantly. And we also considered another data set. It consists of 5 popular social networking sites: Twitter, LiveJournal, Last.fm, Flickr, and MySpace. So the difference of these 2 data sets is that the previous one, the name of the user tend to use their real name on the network, so the ambiguity of name is very significant. But in this data set, this usernames is unique within one social network. So here we can see that the name match baseline can achieve a relatively high precision. But the main challenge here is recall. We can see that our method outperforms the alternative method on both data sets. And to evaluate the effectiveness of global consistency, we conducted an experiment to see that how it goes with our method without the global consistency term. We evaluated this method on both data sets. We call it Cosnet minors. And we can show that without the global consistency term, the performance dropped significantly on both data sets. So finally, with our proposed method, we integrated information from different sources into our A-minor system. We now have integrated personal information from LinkedIn and video contents from video lectures and patent data from USPTO. For like nearly 1 million users on A-minor. Actually, you can go to A-minor, go to your own profile to see how it goes, and hopefully we have got it right. Okay, so thank you for listening. And this is the URL to our system is aminor.org, and the data and source code is here. Thank you very much. I'd love to take any questions. Okay.
So for the local consistency, it seems you need to compare the features for each pair of the entities.
Oh, okay. Okay, sure. Do you have?
How does it scale to the?
Sure. So it's a good question that he asked, how do we scale this method since we need to consider all the potential pairs across different social networks, right?
Across different entities.
Yeah. So actually, in our paper, we described a lot of candidate generation method. We have a set of pruning stage to first generate a set of potential, the high similarity pairs as candidates. So we have a subsection in our paper about this. Yeah.
Any other question? Right, I'll just ask the final question. So clearly that generalizes to sort of multiple sources. Are you also looking into establishing reliability of a source?
Yeah, actually we have been looking at different data sources other than social networks, but it's actually one of our ongoing work. Yeah. So thank you very much.
Perfect. Thank you. All right.